Hello all. Welcome to my talk about running Flink data connectors at scale. I'm Vipul. I'm a software engineer at Yelp. I'm a part of the stream processing team at Yelp. My team is responsible for building stream processors and data connectors, and also other next-level stream processing applications at Yelp. Before starting, I would like to reiterate Yelp's mission statement. We connect people with great local businesses. For folks who don't know about us, Yelp is a local search service powered by a crowdsourced review forum. In this talk, I'm going to give an architectural overview of data pipeline. I'll discuss some of the data connectors which we have built and some challenges which we have faced. I'll go through the integration process and finally talk about how we run so many jobs at scale via a homegrown Flink Supervisor. This is what the data pipeline ecosystem at Yelp looks like. The data sources are either web services or some data store. For folks who are familiar with the streaming paradigm, the streaming engine in this case is Apache Kafka. And all the connectors which we have built are Flink applications which we have built in-house. The protocol which we use in this case is Avro. And a schema registry is an HTTP service which we have built in-house. We call it schematizer, which you can see at the bottom of the screen. This in itself is not just a schema registry. It tracks the schema lineage and also how and where the data is flowing in the entire ecosystem. I personally consider myself this to be like the brain of the entire system. With this architecture in mind, next I'm going to talk about the entire connector ecosystem and how we run a supervisor to ensure data is always flowing and keeping this entire ecosystem alive. Just before going forward, I would like to describe what are data connectors. We have built most of such data connectors on top of Flink. At the end, they are applications that read from Kafka streams, and they add a destination-specific Flink operator to the data stream. One thing I like to call about or emphasize here is that all these connectors by themselves don't do any transformation, apart from the transformation which are specific and necessary for the destination data store. As an example, for Redshift, we don't have flat schema. We use flat schemas at the end. So the data in the schema which we have, we flatten the schema out before copying this data over to Redshift. To have a glimpse of what we have built, here are some of the data connectors. I would classify these data connectors into two parts. The first part, I would like to call them as batch-oriented style data connectors. The first one out here is the Redshift connector, which is a two-stage application to load data into Redshift. The second one is a data lake sink. The general notion about data lake is that it's a single store of raw data at Yelp, which makes data accessible from all processing tools at Yelp. Data lake sink is a connector which is populating the data from different data sources onto the data lake. One key thing to note here is that data lake sink uploads or saves the data in Parquet format at the end. The second kind of data connectors are the real-time data connectors. These either read from Cassandra or sync data to Cassandra. And also there's Elasticsearch. We call it as Elastic Pipe. Going into a bit more detail about the batch-oriented style data connectors, these kind of data connectors help us to archive data, mostly for offline query analysis. The main semantics for this kind of system is that we don't want to have any kind of duplicates or any kind of data loss. Though there have been many systems or many ways to implement this, we have implemented this in a two-staged application. In Flink, as we all know, we have windows and trigger support. We use a global window and a fold function to buffer the data locally. And when some trigger is fired based on either number of messages or some amount of time, we upload this data to S3. And at the same time, we produce a notification message to a Kafka sink, which is consumed by the next stage of the application. And that is a long-running job which consumes this message and either registers or copies or loads this data into the end data store. We utilize this notification message at application startup, thereby using it as an external checkpoint store. The application code in this way looks nicer because there's a clear interface for all the different components. This is a visual depiction of what I just mentioned. So if you can see here, on the leftmost side, you can see all the messages which are coming in. The connector would actually read these messages, and after these triggers are fired, say in this case, after 4 messages, it will upload this file to S3. And then it will also publish to a downstream Kafka sync, where this long-running process would read this data and then do a transformation, and then would take this data and load this data on Redshift or Ethernet Spectrum, or registers it with Glue and Hive. So we implemented this over a period of time, and we had a lot of learnings while implementing these, and we came across a lot of issues as well. And I think this is the right forum to actually talk about these issues, because that's one thing I really want to share about. One of the key issues which we had to fix was around the read after write consistency of S3. We utilized unique key names to get around this. In one of the initial implementations of the data lake sync, we implemented using internal Flink state, where we used to buffer all the data in memory to get exactly one semantics. This, however, caused a very high memory footprint. There was a trade-off, and offloading this entire recovery logic onto an external system like Kafka helped us to get around this high memory footprint of the system. Also, in case anyone has seen stuckness in applications or in Flink topologies, we know that troubleshooting Flink topology is very hard. We had a similar issue where a few consumers were not able to consume partitions, a few partitions, not all partitions, and it actually troubled us for some time. In our case, we chatted with data artisans, and they helped us to get around these stuck consumers. What we had to do was to increase the parallelism of the sink to be the same as the parallelism of the source. In our specific case, we were saturating our internal Flink queues. The second type of data connectors are the real-time data connectors. As what I've mentioned, they consume from data pipeline and sync data to Cassandra or Elasticsearch. We call this internally as Elastic Pipe. That's the reason I've mentioned Elastic Pipe out here. The kind of issues which we started to see with these kind of data connectors were very different. Flink by itself has a very high throughput. And the kind of issues which we saw was that because of this very high throughput, the amount of messages which were going into the end data store, like Cassandra, were actually capable of melting the end data store. To get around this, we implemented QPS per jobs so that we can throttle the amount of information which is going to the end data stores. One key thing to note about these real-time data connectors is that the system which we have built only allow upserts at this point. We utilize Flink's internal checkpointing to commit these offsets back to Kafka. As in comparison, in the batch-oriented style, we use an external state store like Kafka to save this information. In this case, we use Flink internal checkpointing. This ensures that the connector will only commit offsets until all the in-flight requests have been acknowledged. This helps in application recovery and makes the application restart from the last fail-safe point. I have some Slack notifications coming in. Just ignore them, please. So we have learned a lot building these various data connectors. And we have seen a lot of issues where it comes to sharing issues or metrics. So to ensure an homogeneous interface across these different connectors, we have built guidelines which application developers need to follow. We have built a cookie cutter project which ensures a common template for these connectors, which ensures, in turn, a common set of metrics and patterns, and a common way to do process discovery and alerting. All data connectors are mandated to have auditors to have data integrity. Also, they need to have support for most Avro types. Data is a core part of our infrastructure, and we ensure that data is well audited and well within the semantics of the system. A few systems have exactly once, a few systems have at least once guarantees. Black box auditing is an essential technique which we employ to verify the behavior of every individual component within the Yelp's infrastructure. It's very useful because it does not, because we do not rely on any assumptions which we have made while building these data connectors. We run auditors, I have mentioned, at regular intervals of time to ensure that we are maintaining the data semantics across these connectors. And all these results are available on a global auditor dashboard so that all the folks in the firm have visibility. This is a sample auditor dashboard. Just to, and these are the various data connectors which we have built, the auditors which we have built. Just to go over the legends, green is that the audit was passed, red is the audit actually failed, and all the gray boxes which you are seeing is, for some reason, these audits did not run for those specific days. In the case where the audit is red or the audit did not run, the on-call person for those specific teams who is owning these data connectors is responsible for troubleshooting and seeing what happened. So before going further, I would like to sort of go down into one of the auditors which we have built. So for the first example I would like to take is for Data Lake Auditor. What I mentioned before, Data Lake Auditor, what it does at the end of the day, it takes a file, reads from data from Kafka, takes this data and uploads them on S3 in Parquet format. We run multiple audit modes. One is the fast mode, the next is the metadata mode, and the slow mode. What we do in the fast mode is that, if you remember, I mentioned about the notification message. So for every batch of file which has been put to S3, we have this message which has the start of information of the start offset of the batch, start offset of Kafka of this batch, and the end offset of Kafka. What we try to audit in the fast mode is that end offset plus 1 of one notification batch is equal to the start offset of the next batch. If it is there, then everything is fine. Otherwise, we have these two cases of missing messages or duplicate messages. The second audit mode, specifically in the case of metadata mode, what we do in this mode is that we read the Parquet file. So the Parquet files in itself, they have some metadata information regarding the kind of data which we have uploaded. We save the Kafka offset in the Parquet files itself, and we audit that very similar to the same way we audit in the fast mode. The last mode is the slow mode. This is slow mode because it's actually very, very slow, and we run it only when the fast mode and the metadata mode fails. What we do in the slow mode is that within each file which we have uploaded, we read the entire file line by line. So every line is basically corresponding to a Kafka message. We read this entire file, and we read the same data from Kafka, and we correlate one-to-one is all the data matching. As you can imagine, because it is reading from Kafka, and we are trying to correlate each and every message, this is very slow. One key thing to know about the Elasticsearch auditor, which I'm going to talk about next, is that every time we upsert a document, we add this metadata information in the document. So in this case, if you can see that there's some offset 55. So this corresponds to the corresponding Kafka message which we have of which document which we have uploaded. The Elasticsearch auditor reads. How it works is that the Elasticsearch auditor reads from the upstream Kafka message and collects all the unique IDs of the message. It then looks for the IDs in Elasticsearch by using a binary search algorithm to search over the range of IDs at a time. One thing to note is that so that the auditor is not negatively impacted by new data which is coming in, we only consider, in Elasticsearch, if there's any offset beyond the high watermark of the upstream at the time when the auditor is run, we ignore these specific offsets. That being said, we are in the process of rewriting this auditor because to make it more scalable. Right now, because of this binary search algorithm which we run on Elasticsearch, it's a bit memory intensive on Elasticsearch. So we are trying to reevaluate and rewrite this auditor. In our architecture, data connectors have a primary role. Developers, most of the time, get the data into data pipeline, mostly with the intent that they want to have this data into some end data store to power some business critical application. Users can set what we call as data connections. This is basically telling the system to ingest some data from some data store by using a command line interface tool. As you can see here, you can add a data connection. You can list which all data connections are there, and you can also remove or disable these data connections. The connections are managed by the schematizer. And the data connectors are instrumented by schematizers for what data needs to be ingested where. This goes back, as I mentioned, like for what I believe personally is the schematizer is the brain of the system. It actually sees where the data is moving in the entire ecosystem. So next I want to talk a bit about the Flink Supervisor. How we do application deployments at Yelp is that we utilize a multi-tenant cluster per data connector. What it means is that we have multiple jobs running per Flink cluster for a given data connector. Jobs are maintained by this long-running process, which is the Flink Supervisor, which interacts with the Yarn application and takes care of scheduling jobs, alerting, monitoring upon job failures, and interacting with Schematizer to control these various data connections. A bit more into detail about how the supervisor works is that supervisor polls at regular intervals of time. In our case, we poll every 5 minutes to see if there are new data connections which have been added by users or clients inside Schematizer. Supervisor also groups these data connections based on a DSL. So what I mean by a DSL is that inside Supervisor, for a specific data connector, clients can specify that I want all these connections to be grouped by a specific data store name. Let's say it's Redshift or Parquet. What a supervisor will do in this case that it will take all these connections and group them and then send them over to the end application. This overall helps in the logical grouping of jobs based on user-defined patterns and also allows multiple streams to be written in a consistent way via these Flink jobs. All these different infra components tie together and help us build the entire ecosystem here at Yelp. We currently run over 1,000 long-running jobs, which are connecting data to various data stores. So in prod, we have around 10 different multi-tenant clusters, and we support 5 different kind of data connectors. I think that's all from my slide. I also finished a bit early.
Are there any questions? No questions? Ah, there is.
Do I get it correctly that the point of the auditing is just for you to know that the systems are working correctly?
It's twofold. One is that the systems are working as we expected, and also that the data at the end is like the integrity of the data is maintained as what the users are expecting. We are not losing any kind of information, or we are not deduplicating the information in the entire pipeline.
Yeah. But it's not like the audit is someone has changed this record. It's a different kind of audit.
Yeah.
Okay.
Other questions? No? Okay, then thank you very much, Vipul.
I think we do have one more.
Ah, one more, okay.
Hi, I was just wondering what you found to be the most challenging part of implementing a new data connector.
So I think the reason why we went towards the cookie cutter project and sort of making a common interface for people was mostly around that the amount of time initially we had spent across, anytime anyone was building a Flink application, you had to go around all these shading issues, which were there in Flink 1.3 and I think in 1.4 also. Also, like, deployment of this infrastructure we run completely on EMR, on Yarn. So when everything used to run fine locally, but as soon as we went to a cluster, stuff used to break. People used to configure their own set of metrics. So it was kind of all over the place. So basically to systemize that into one common flow, that was the hardest part. And yeah.
Other questions? Okay, then thank you very much.
Thank you.